All right, so today is March. How do you like that? March the 1st. And we're in heat exchanger design. These problems are a lot longer. They take a lot more effort. So I'm passing out a problem. What we're going to do is we're going to basically not just delay, but we will just delete DEL. We'll delete homework 11, and I'm handing out a modified 12. So the handout that I just gave you is the top of the front page. It says homework 12. Okay? So this will be due March the 3rd. If you did problem chapter 3, problem 11, you want to turn it in, I'll give you credit for it, but don't go do it for extra credit. You don't have time. Okay? So let's talk about this problem that'll be due next time, and we'll work on it, okay? So I have a Word file here, and here's the problem. So it's a cross-flow heat exchanger, and I took a figure out of the book to illustrate. And you have a printout in front of you so you can annotate on the illustration. So let's take a look at what they show us in this illustration. They show us a length scale 1, a length scale 2, and a length scale 3, do they not? And they show us the fluid 1 flowing in that direction, and they show the fluid 2 flowing down. And these cross-flow heat exchangers have little packages or sections where it's a heavily finned surface that is in between where the fluid 2 flows through as it goes down the passage. And then there's a little thin plate that separates it from the other heavily finned surface, surface 1, where fluid 1 flows through. Now they're only showing one of the channels. And what you do is you have a number of those passages. So you may have 10 for the fluid 2 to go through, and then 10 for the fluid 1 to go through. They come in packages. Okay. So let's take a look at the information given. They tell you something about, okay, if you don't know how to calculate the volume of a cube, L1 times L2 times L3. Okay, I think you could have figured that out. That's the size, the volume of the heat exchanger. And then fluid 1 frontal area is L2 times L3. Do you agree? The fluid 1 frontal area is L2 times L3. Thumbs up if you agree. All right. And then what is the notation? They're showing you F of R is a subscript, comma 1, so it's a frontal area. How about the fluid length 1? What does that mean? That's the length of the passage through that compact heat exchanger that fluid 1 flows through, that length. Do you agree with that? Don't skip the little details. We're going to spend all day on this, or the next hour on this problem, and don't overlook the details because you can easily get confused. So L1 is the length. You know what? That's going to affect the pressure drop, isn't it? That's going to affect the pressure drop in a big way. How about the fluid 2, the frontal area? The total frontal area coming down is L1 times L3. Do you see it? Do you agree? And then the fluid 2 length that it travels is L2. Okay. Let's continue to read. Okay, or you can mark on this. This is example problem 3.5 in your textbook. This is example problem 3.5. So if you brought your textbook, I thought I would just spend time working this example problem. One of the problem that I had assigned would basically, it's just like the example 3.5. Problem 11 is just like it, but we're not going to solve that one and turn it in. Basically, you're going to redo this problem because there's a whole lot of detail given in the textbook to help guide you through this long, elaborate calculation. So I didn't change hardly any numbers. So fluid 1 comes in at 2 pounds per second. It has an inlet temperature of 200 and an outlet temperature of 100 degrees F. Is that the hot fluid or the cold fluid? Is the fluid 1 hot or cold? hot because it's cooling down and it's air. So you can make all sorts of annotations on your sheet. It flows through a 17.8-3/8 W wavy fin plate surface. What are they describing? That finning in between on that compact heat exchanger, that flow area that it flows through. The fins are made of aluminum alloy, and for some odd reason they use this value for aluminum, so we'll stick with it. K is 115 BTU per hour foot degree F, some alloy. The inlet pressure is 16 psi, and the desired pressure drop is 8 pound-force per foot squared. Okay. Fluid 2 is air. The inlet temperature is 50, the outlet's 150. It flows through a 9.03 plain fin plate surface. The fins are made of aluminum, same material. And the inlet pressure is 16, same inlet pressure, but the desired pressure drop is 35 pound-force per foot squared. The parting plate is made of aluminum and the thickness A is 0.0015. What do they mean by that plate, that parting plate? What's it separating? It's separating the two heavily finned sections of the flow passage for fluid 1 and flow passage for fluid 2. Maybe it's a good time to make a sketch. Maybe, well, let me wait on that because I didn't turn this into a PDF, or not a PDF, a journal. Let me turn it into a journal if it works. Sometimes this does not work. And hey, it looks pretty good, doesn't it? Hey, that looks like it worked out pretty good. So we'll scroll down. Now I can annotate. So basically, there is a thickness of the plate right there in between them. Make sense? Okay. The heat exchanger has been designed, and these are the values given, worked out in example 3.5, where L1 is reported to be this, L2 is this, L3 is that, and hence there's 12 passages. N is equal to 12 for each airstream. So it's like 12 sections that have one downflow and one crossflow. Okay. Will the heat exchanger work? That's your question. Check the design by making some calculations. At a minimum, check U and A. Calculate UA. Calculate Q, the rate of heat transfer. You're saying, hold it, you told me the inlet and outlet. Well, don't calculate it from the m dot C sub P delta T of the two streams. Calculate it as if it's a heat exchanger, knowing only Tn of the hot and Tn of the cold, and you calculate how big it is thermally, UA, right? And then it's a cross-flow heat exchanger, so you can use the effectiveness NTU method. And then calculate that exit pressure. Is it only, for stream 1, is it only 8 pound-force per foot squared less than the inlet pressure? Is it? And the same for the exit 2s. That's what I mean by, will this work? Do you see the questions you're answering? To help guide you, because this can be quite complex, is I tried to abstract and put on the second page. Maybe I shouldn't have done double-sided, but I did do double-sided, so you have to turn it over. And you can see this is for that wavy plate fin, wavy fin. There's a lot of information. Hopefully we can read it. And I grabbed an illustration off the internet that helps clarify, but it's in millimeter, and I didn't convert everything back. So, but they're consistent. It zooms in. What this illustration here does is it zooms in here. So it helps you see it. And then this is for that surface 9.03, and they're zooming in right in here for the detail. Okay. Now, let's go to the third page that I have, and all this page is to help step through the process. Step through the process. So something like, tell me, and I just put a few of these in random order. I mean, not completely random, but tried to put some logic to it. But it doesn't. If you just fill this out, it won't take you to. It's not the road to the yellow brick road to the wizard's house or something. You got to do other calculations. Okay. So but this is what I mean by this. What's the outlet temperature? So in what units? Well, I think we're probably going to report it in degrees F. All right. And now you say, hey, that's an easy question because it was given in the problem statement, wasn't it? So what is the outlet temperature for the fluid going through? Isn't this side 1? Isn't this fluid 1? Does fluid number 1, which I wrote 2. I can't even write what I'm trying to say. Fluid 1, doesn't it go through the wavy fin? Okay, if it goes through the wavy fin, what is its outlet temperature? 100. And then this is for fluid 2. I purpose to put the first line pretty easy, isn't it? Flow. What's the outlet temperature of fluid 2? 150. All right. Now, what is the expected outlet pressure? We didn't calculate it, but what's the outlet pressure that's reported in the pressure in the problem statement? And here I have the units written here, so it's you don't have to repeat them, but they're the same units right there. So it's what is it going to be?
8.
But that's the pressure drop of 8.
16.
But you have units of PSI and pound force per foot squared. So one of these you will use a little bit today. If you have a calculator, please get it out. And I give you some space to make that calculation. What I'm going to do is I'm going to pause, and I'm going to walk around and watch you and help you solve some of these and answer some of these questions as we go, okay? All right, so we got 2296 pound force per foot squared. Let me get a couple thumbs up on that. Couple there, very good. And how about for the second fluid stream? 2287 point something. 2269. Oh, it's 2269. Sorry. Looked at the wrong spot. Thank you for the correction. All right. Now the average mean temperature for those that challenged on that one. This would be easy, right? It comes in at 200, goes out at 100. So what is it for the first fluid stream? 150? And this is degrees F. And this was lbf per foot squared. How about for the second fluid stream? Fluid stream. Comes in at 50, goes out at 150, so it's 100. Now, what about the average pressure in pound force per foot squared? So, what's the average pressure? Well, it's going to be higher than 2296, isn't it? 2300? Right? And how about for the average pressure? This is by 2287, I believe. Is that right? I don't want to leave anybody in the dust. I want you to make the calcs on your own. All right, so now a little bit of time. I'm going to stop and let you calculate the mean density of air. At what temperature, at what pressure? At the temperature of 150 and pressure at 2300, or the temperature of 100 and 2287. And you're going to use an ideal gas equation, something like rho is equal to what? P molar mass of dry air divided by R bar T. Does that equation look good? I mean, ideal gas equation. I know that a lot of times in fluids we use rho, and a lot of times in thermo we use the inverse of rho, specific volume. And What about R bar? R bar, there's a number of units for it, but the one that makes most sense would be 1545 foot, can't write, foot pound force per pound mole degree R. Oh, Professor, I don't like pound mole. I know. The molar mass of dry air, 28.97 kilograms per kilomole. It's also 28.97 pound mass per pound mole. Professor, I don't like degrees R. I know. The temperature in degrees F, if I want to get it into degrees R, what do I need to do to the temperature in degrees F? I add 460, exactly. So with those pieces of information, I think everybody should be able to calculate the mean density. I'm going to pause. All right, so let's pick it up here. Let's see, what did we get for the density of the fluid that's hot going through? Some people calculate 0.0712-ish, in that vicinity. And that would be pound mass per cubic foot. Actually, it's a little different than that. I did it a different way. So what do you get? 0.707. Oh, there's another zero, yeah. 0.0707. That's pound mass per foot cube. And then how about for the density of the second fluid? 0.0765. That looks about right. Okay. Now, this one is just reading the diagram. This one's easy. The spacing between the plates. Okay, and we want it in feet. And on that diagram, it may be in inches. On the diagram that I gave you, it may be in inches. True? So I'm going to pause and let you read that diagram and get the spacing off in feet. So the plate spacing is this, 0.0413 inch for the wavy. And if I come up here, what are they showing me? Is this the plate spacing on that side view? Is that the B? Yeah, that's the B. I know this is in millimeters, but if you want to convert that millimeters to inches, you'll see that that's 0.413 inch. True? And now I need that converted to feet. How about the next one down here for the 9.03 surface? Well, it's 0.823 inch. So one of the things is that I didn't put it where you could see it, but this one here has a B of about 0.4 inch. This one down here has a B of about 0.8 inches. It's about double. Isn't it twice as big? The gap. So, okay. So let's go back down and put the numbers in. So we wanted it in answers in the answer of feet. And who wants to give me that number? 0.3442 and 0.06858, something like that. All right, what is now the volume between the plate for each of those? What's the volume of one passage between? So you could really divide this, the volume that's between the plates. You could say I'm going to do it for one passage, And then I'm going to do it for 12 passages because I really have 12 in the whole heat exchanger, don't I? Or you can just do one passage and then know, hey, if I need it for the whole heat exchanger, I'll multiply by 12 in a second. So the volume between the plates would be that B times an appropriate area. What's going to help you get the area? That first illustration with the L1 and L2 and L3 dimensions given. And so for the first one, the volume for one, it's B1 times V2, it's B1 times L2, L3. Did I get that right? Is it B1, the thickness of that first passage, times, because this is like a B1 and this is like a B2. Thinking about sides, side 1 and side 2 of that compact heat exchanger. Forget about trying to put too many numbers in there. So this is for side 1, and then for side 2, it'll be V2. The volume between one plate is the width or the distance between them, B2, times L1, L3. No, it's not that, is it? No, it's not that. I'm sorry. You figure it out. I'm tired. I'm trying to do too much and not look at, I need to look at the illustration. Right? So the volume 1 is B1, I had that right. L1 times L2, exactly right. There, thank you. And then V2 is B2 times L1 times L2. All right. Now, if you wanted to, you could calculate the total volume for the fluid passage 1, just multiply that by 12. The next line, what is the fraction of the heat exchanger volume that's occupied by the wavy for fluid 1 to pass through, and then the 9.03 for the second fluid to pass through? What is that fraction of the heat exchanger volume? All right. That's what you do for that question is you really need the illustration. And let me say this. How many passages did we have in this problem statement? 12. Okay. So we already calculated the volume from side 1 for one passage. If you multiply that by 12, you get the total volume, these are all volumes, for that fluid 1 can go through on side 1. And then you had the volume for side 2 for one passage. Didn't we just do that? And you multiply by 12, this is for one passage. And then you get the total volume of this heat exchanger that's devoted for side 2 for fluid to flow through. The only thing is I'm going to have how many plates do I have for each little block of passages? I'll have a plate here and a plate here. Well, what about the topping plate to seal it? Well, that's 2 of them with associated the next block of passages, and we're going to have 12 of them. So the total number of plates is the number of passages times 2 plus 1 because you got to seal it at the edge. Make sense? So the volume of one plate is simply the thickness of one plate. I think they used the letter A. A, let me scroll down. Did I use the letter A in this problem statement? The thickness of the parting plates, one parting plate has a thickness of 0.0015 foot. Okay, so we did use the letter A for that. And then the dimension is L2 times L3. So that gives me the volume of one plate, and then I can percolate that to get the volume of all the plates. Would be the number of plates times the volume of one plate. Okay. And so let me go. I know that this is around, for the first fluid pass, is around 32%. Is that what you calculated? Then around 65%. Is that about right? And then for the plates is not quite negligible, but it's close to being negligible, around 3%. That makes sense? Okay, so let's scroll back down and put those numbers in and proceed.
Can you explain how you get, so you just divide this, how did you get that?
Okay, which one?
Like any.
Well, we have 12 passages. So when I'm coming in for fluid 1, I'll have a passage like this, a passage like this, a passage. And this, they're showing you just one of the passages right here. Let me change this. This is just one of the passages that fluid 1 can go through. But we're going to have 12 of those. So I just calculate that area of one passage multiplied by the depth, get the volume. So I got the volume of one passage, then multiplied by 12, and that gives me the total volume in this heat exchanger, which is devoted to letting fluid 1 stream go through. And it's actually 33 or 32% of the volume. Total volume, of the total volume. Oh, how did we get the total volume? Yeah, it's right here. L1, L2, L3. And then the same for the other passage. So I have 12 of those for a surface. But the tricky part is how many plates and how much do they occupy. And for every package of 2 passages, I have 2 plates, and at the end I have an additional plate. So 2 times the number of passages plus 1 gives me the total number of plates. The thickness of the plate, the area of the plate gives me the volume of one plate. Multiply that by the number of plates, and I have the volume of all the plates. So I sum those up. It should be close, but I don't think it's spot on with L1 times L2 times L3. I think it's close with the book, but I don't think it's spot on. Okay. Now the next question is what is the frontal area? Sometimes FR, subscript on A, sometimes FF or FT. So what is that frontal area in foot squared? This is not a hard question. It's just the fluid's coming at that front surface. And now, what is the total frontal area? Then later we'll get down here the minimum free flow area, which is a little different than the frontal area. So what's the frontal area for fluid 1? Is it 5.9? 5.74? is the frontal area for fluid 1. You could calculate it by L3 times L2, or you could get it by the number of fluid passages, time, which is 12, times B1, how wide it is, times the height of it, L2, right? I don't think they're going to give you exactly the same, but they'll be close. Because I don't think L3 is consistent.
Might be like 5.9.
5.9? Okay. 5.9. And then you do the same thing for the frontal area. Now, while we're here, let's just skip down and do this one. You have the frontal area coming at it, but then there's the area for the flow to continue through the heat exchanger. That's the minimum free flow area for fluid 1 stream and fluid 2 stream. What is the minimum free flow area? It's not going to be 5.9, it's going to be less, isn't it? But how do I calculate that? Minimum free flow area. We're going to work right here now for a second. And guess what? There's a sigma, which is the area, it's the ratio of the minimum free flow area divided by the frontal area. It's given on page 224. So if you want, I'll tell you what, you can just go and get that equation off of 224, calculate sigma, then multiply sigma times the area frontal that we just calculated, and you'll get the area of minimum free flow. So let me give you the equation for the sigma. The minimum free flow area divided by the frontal area. I'm sorry, it's not sigma, it's alpha. Alpha. All right, so the equation is alpha is equal to B, I'm just going to do it for alpha 1, B1 beta 1 divided by, and then it's the sum B1 plus B2 plus 2A. I can understand the B1 plus B2 plus 2A. That's like looking at the width of one whole section. B1 plus B2 plus 2A's. Those are the thickness of the plates. But in the numerator, you have B1 times beta 1. And beta 1 is a property that's given in our problem. Let's jump back up, second page. Where is a beta for this compact heat exchanger? Five one four. Right. I messed that up. I'm sorry. This is the equation for ALPHA, alpha 1, but alpha 1 isn't the minimum free flow area divided by the frontal area. That's the area heat transfer per volume of the heat exchanger. Sorry. That's the area heat transfer to the volume of the heat exchanger. What I'm looking for is sigma, S-I-G-M-A, from page 224, which is the alpha 1, which you calculate, times the hydraulic diameter divided by 4. So an intermediate step is to calculate the area of the heat transfer divided by the volume, that's alpha 1. Do I put that anywhere? Area heat transferred by the total area is given. area heat transfer. Well, we know the total volume, don't we? I should have put an alpha in there. Let me do that. For your alpha for this heat exchanger, it's about 167 foot squared per cubic foot. And for the flow passage 2, about 158. Those are correctly calculated on page 224 of the textbook. And then the sigma, which is the ratio of the two areas, that's what I wanted to get to, is 0.2904 and 0.600. So around 30% and around 60%. So think about it. As you approach for fluid 1, that whole area, that whole cross-sectional area, it has to get down into 29%. That's the free flow area divided by the total frontal area. But the other one, for fluid 2, it has 60%. All right. So now the minimum free flow area of the heat exchanger, that's just going to be this sigma. Let's say just do it for 1, times the area that 1 sees as it approaches, the total frontal area of 1, area frontal of 1, which we calculated up here. That gives us the area free flow, or area C. They use different notation, AC1. I have to get that minimum free flow area correctly. Okay. So what do we get for the area minimum free flow area for the, what do you get? 4 point?
No, I got, well, it's sigma times the frontal area, correct?
Yes.
So I got 1.713.
Yeah, okay, and that's in foot squared. 1.713 for the frontal area. So many of these little calculations. All right. Then how about that heat transfer area? Well, you go back to alpha 1, which was the area heat transfer per unit volume, multiply that by the volume, and you'll get area heat transfer 1. Let me take a look here. Okay. Some of these don't really explicitly calculate and report them.
Is that volume the total volume?
Yes, total volume.
Is the number for that big, like large?
Yeah, it should be pretty big.
Which volume you said?
The total volume. The total volume. All right. Well, what number do you get for that one? That's a foot squared.
That's 696.223.
Yeah.
Yeah, I got this.
Yeah, it's around that. Yep. 696. And it should be about the same for the other area, for the second one too. Yes?
For the frontal area, I understand if you do L3 times L2, you get 5.9. Why if you do 12 times the spacing, B1 times the length, you get nowhere near that?
This is the number, you're saying this is 12
Yeah.
times, oh, this is not the frontal. That is, if I do 12 times B1 times L2, that gives me the free flow, or close enough to the free flow. It should be close to that. But no, this was L3 times L2, right? No. No, this is not right at all. Just do it, forget that equation. The frontal area is L2 times L3 for the area frontal of 1. Yeah. All right. What there is there's a little blockage of that finning surface within the passageway. All right, the area of the fin to the area total. What is this area total? The area total for like heat transfer. So what you're going to find is what percent of each of those passageways where that fluid 1 is flowing through, that it can transfer heat, what percent of it is the area that the fin is. All right. And that, let me go back up here. And that is right there, isn't it? Isn't that the finned area divided by the total area? So most of what the fluid sees as it flows through that passageway for fluid 1 is 90% or 89.2% of it is the fin surface. What's the other 11%? Well, it's the bare. The bare. It sees a little here and a little there, but mainly it's seeing this surface, both sides, that side, that side. Make sense? So that number, we just report the fin area to total area, 89 point. So that's the 0.893, whatever it was. Okay, if you assume that the fin efficiency is 90%, which is a pretty good guess, so to speak. I know that you can do it brute force, but I wanted to not spend too much time bogged down on calculating a single fin efficiency. So let's just say it's 90%. Then what is the overall efficiency for the surface that the fluid flows over? Made sense? So, sure. It was just reported. Yeah, it's just, well, 892. Did I read it wrong? It's 892. Thank you. So I'll fix that right there. All right. So what is the equation for the overall surface efficiency? 1 plus, minus, etc. One minus the area fin to the area total times 1 minus the efficiency of that individual fin. If you put in 90% and you put in, what was this? Almost 90% again. So you have 1 minus 90% times 10%. And it's a little higher. It's a little higher than 90%. What does it come out to be? 92? .9108. Okay, so let's put 91.1%. All right. We're going to need that when we do the heat transfer, but okay, at some point we're going to have to get the mass velocity, G, for each of those passages. What's the mass velocity for each of those passages? We know the total mass flow rate, don't we? Don't forget that that was 2 pound mass per second. That's in the problem statement. So what is our mass velocity? I'm going to pause. All right, so the G is equal, or G1 is mass flow rate 1 divided by the A free flow cross-sectional area, or that minimum area. So that's this area right here. A free flow for 1. So it was 2 pound mass divided by 1.713 foot squared, something like that. That'll be for 1. How do I get the Reynolds number? How do I get the Reynolds number?
G over viscosity times diameter. I mean G times the diameter over viscosity.
Yep. So G times the hydraulic diameter divided by the viscosity. Now the viscosity is given in the textbook. I didn't redo it here, but what about the hydraulic diameter? Did I ask for it in any of this above? I should have if it didn't already. Is it up there somewhere?
It's on the notes.
It's on the what?
It's on the notes. It's there as well.
Yeah, right here, the hydraulic diameter. Yes, and it's right on your sheet. That hydraulic diameter is given. So it's flow passage hydraulic diameter is given right there. Should I go back up? Right here for the second passage, etc. All right, you get really good at going back and forth. Okay, now I need this information. Go get it. So we calculate the Reynolds number, and if my memory is correct, this should come in around 600 or so. What do they get the Reynolds number to be for that first flow passage? A little below, I think. Can you find it? Can't find it. Terrible, 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 terrible. Should have wrote it down. Well, I have it somewhere. Okay, 598. So it's right at 600. 598. And then for the second flow passage, it's 3040. Now, they ask you to get the Colburn heat transfer factor and the fanning friction factor. Well, guess what you need to get those off of the plots? So if you can remember 6,000 and around 3,000, we'll scroll back up and we'll take a look here. And 600 is right in this vicinity, isn't it? And so to get the Colburn heat transfer factor, that's the bottom line. See, this is the Colburn heat transfer factor, sometimes J sub H written that way. And so we read it off and 0.015, roughly. How about the fanning friction factor? It's right here. So it's a 0.075. 0.075. I know it's open for debate, but 0.015 for J sub H, and friction factor fanning is 0.075. Um, all right. Okay. Let's take a look at that was for the wavy. How about for the one with this passage, and it was around a little over 3,000? So what is the factor? 0.03? No, 0.003, sorry, 0.003 for J sub H. And what about the fanning? It's around 0.0098 or 97, something like that. Just a little bit below 0.010. This is fanning friction factor. Oops. Okay. So let's scoot down. I see them. So those values we got off of our charts. How are you going to get H now? Finally, I need H. Oh boy. I wish I could give you more time to think through it, but I'm looking at the clock now and I felt like, but how do I get H? Using that J sub H. Using, basically this is equivalent to the Nusselt number right here. This Colburn heat transfer factor. What was it defined as? Look at that plot again. J sub H. I know they don't use the J sub H, but they define it as what? H divided by G C sub P Prandtl to the 2/3. Is that what it is? It looks like it. I know you have to have good eyes. So once we had a Colburn heat transfer factor, that's how you get H. You get J times G times C sub P divided by Prandtl to the 2/3. It's just like you said, get the Nusselt number, then unravel it. Well, this time it's embedded in what they call the Colburn heat transfer factor. All right. Oh boy. Boy. I'm running out of time, but we're almost done. How about this? What I do is think about one plate separating half. Here's a fin surface on this side, and then there's, I know it's flowing the other way, but I'm going to show it like this too. A fin surface on that side. And what I do is I look at the symmetry section and the symmetry section to get the fin thickness to be the half B, or the fin length to be half B because of symmetry. So as the fluid one, I'm going to just show it like this maybe, flows down this passageway, half of it goes to the left and half of it goes to the right. When it goes to the left, it goes through a plate, then it to the other surface, the other fluid passage. If it, just look at it this way, it'll go to the right. Think about that. It'll go through the wall or the plate, then it'll go through the fin to the other half of the fluid. I know the other fluids come in this way. Okay, so what I need to do is I need to get the resistance thermal for this segment, then the resistance through the plate, then the resistance, the fin convection off. So what is that resistance? Isn't it 1 over the overall efficiency times the convection coefficient on that side times the area heat transfer on that side? But be careful because half of it's going in one side. So the area heat transfer for a passage, let's say you find the area heat transfer for all of that fluid 1 sees, divided by 12, now I have it for a passage. Divided by 2, now I have it for 1/2 of that passage. All right. Then we have the thickness of the slab or the wall or the partition. They were using the letter A for it, fine. The thermal conductivity of it. And then we have that area of it. That area is like L 1 times L2, the area of the partition. Okay. Then we're going to have, just on the other side, some efficiency, some convection coefficient, and the area heat transfer on that other side. There are different areas of heat transfer, and again, that's half of it, of one passage, etc. So, so what I like to do is I like to get this resistance for this term right here. This one is negligible. You can make the calculation. It's truly negligible. And then for this side right here, you can make the calculation again. So you're going to need the efficiency for both sides, the area heat transfer of both sides, the convection coefficient of both sides. And now if I sum those up, I get the total resistance. It's 1 over UA. What is the A? It's whatever. It's matched with the U. And when we go back up, it's in our overall heat effectiveness NTU method. UA is a parameter together. Okay. So you got to do it for both sides. This side, that side. Neglect the middle, and you can get the overall heat transfer coefficient. Okay, I left out about the pressure loss. How do I calculate the pressure loss? Neglect the inlet and outlet and acceleration effects. The only thing you think about is the core effect, the pressure loss in the core. What is our pressure loss equation? I got about 2 minutes. What's our pressure loss equation? It would be the pressure drop, or the pressure loss, is G squared divided by 2 rho G sub C, if you want to make sure you don't mess up the units, times neglect the entrance, neglect the flow acceleration, neglect the exit, just the core. It'll be the fanning friction factor, that's why we needed to get it, times some area for the heat transfer, which is the same area that gives us the resistance to flow, divided by the area of free flow, which comes in that equation they use AC. That's why up here it's like, AC versus AFF. It's the minimum free flow area in that equation times the density of the fluid coming in divided by the mean density. Well, guess what? Just say that these two densities are the same. It's not that strong of an effect. I already threw out the inlet, the outlet, and acceleration term. You get that fanning friction factor, and you'll account for at least 95% of the pressure drop for this problem. So that gives you the pressure loss, or the pressure drop, for each side. There's about 5 or 6 pages of this problem, example 3.5, worked out in the textbook. All I ask you to do is to go back and say to yourself, can I calculate the UA? Can I calculate the rate of heat transfer? Can I calculate the exit and inlet parameter pressures based on those dimensions? So what you're going to do is you relax the outlet temperature. I mean, you designed it assuming I want to achieve these outlet temperatures, and you relax the desired pressure drop. And you just say, what am I going to get for the actual pressure drop? And what am I going to get for the actual rate of heat transfer, which will dictate the actual outlet temperatures? It's a challenging problem. Thank you very much for your attention.